Good morning, everyone. I am sure you're all curious to hear about the Sherlock Holmes-like research topic that our next speaker, Dr. Roy Gerona, will talk about today. And before I introduce our speaker, let me share a short story about Roy's research work. A couple of years ago, you probably remembered sometime in 2017, where there's a news of a drug epidemic in the US describing users of a new drug called AK-47 24K Gold, causing some zombie-like symptoms among its users, leading some witnesses to describe the effects of the drug as a scene similar to the Walking Dead TV show, the popular show about zombies. This has baffled the authorities in the US, leading the US Drug Enforcement Agency, the DEA, and the Department of Homeland Security to contact Roy Gerona's laboratory to solve the problem. In fact, the importance of Roy's research on designer drugs, detection of designer drugs, has led him to be featured in a Netflix TV series. So before Roy became a TV star, let me give you his professional background. So Dr. Roy Gerona obtained a PhD in biochemistry under a Wharton Scholarship at the University of Wisconsin in Madison in 2008. And prior to going to the US for his PhD studies, Roy graduated cum laude from the University of the Philippines, Los Baños, with a bachelor's degree in chemistry. He also worked as an instructor at UPLB while pursuing his master's degree in biochemistry. So after his PhD, Roy went to the University of California, San Francisco for a postdoctoral fellowship in clinical chemistry. He is currently an assistant professor at the same university, University of California, San Francisco, and at the School of Medicine. So he's an assistant professor at School of Medicine, UCSF School of Medicine. He also manages the Clinical Toxicology and Environmental Biomonitoring Laboratory and the Tuberculosis Hair Analysis Lab at the same university. Roy has received numerous honors and awards for his outstanding research work, such as the TB HIV Research Prize and other awards, too many to mention here. He has also published extensively with more than 100 publications under his name. He published in prestigious journals. So please join me in welcoming Dr. Roy Gerona. Roy?
All right. K2 is a street name for legal drug products containing synthetic cannabinoids, one of the 12 NPS or new psychoactive classes, which have been on the rise in the United States and the world since 2009. So what are new psychoactive substances and why are they a huge problem in public health and lab testing? NPS are substances that have similar effects to drugs under international control, but they themselves are not scheduled. They can either be a structural or functional analog of traditional illicit drugs like cannabis, heroin, and methamphetamine. Examples are herbal incense or synthetic pot, more popular known in the United States as K2. In Europe, they're more popularly known as spice. Bath salts is another example. These are comprised of synthetic cathinones, which are potent alternatives to methamphetamine and cocaine. And more recently, opioid analogs, which are primarily comprised of fentanyl analogs, have become popular too. NPS are popular to recreational drug users primarily because, one, they have become cheaper than traditional illicit drugs, at least here in the United States. Second, most of them are not detected in routine drug screen. And third, when they're initially introduced into the market, they are not scheduled. So you can sustain a recreational drug habit without the fear of legal repercussions. However, because little is known about their toxicity and relative potency, as well as the consistency by which they are produced, this group of drugs have caused numerous mass outbreaks and countless deaths, unfortunately. In lab testing, the rapid evolution of the chemical identities of NPS have posed an insurmountable challenge among clinical labs. Development of drug assays here in the United States is highly regulated, similar to what is true there in the Philippines. Typically, it takes about 4 to 6 months to develop and validate an assay for drug testing. And in fact, it takes about a year to implement that newly developed test clinically. However, at the height of the synthetic cannabinoid epidemic, clandestine labs that are producing these drugs are releasing new drug products almost every other month. Hence, by the time that the new drug test is finally implemented, clandestine labs have already moved on to at least 2 or 3 newer generations of synthetic cannabinoids, making the drug test really irrelevant. So NPS has been increasing in numbers since 2009, as shown in this graph, which was presented at the 2020 World Drug Report from the United Nations Office of Drug Control. By the end of last year, about 950 NPS have been reported to UNODC, and more than 80% of that have just been identified in the last 10 years. In the United States in 2018, about 5% of NPS accounted for the drugs that were reported to NPSs. And that is likely an underestimation, primarily because NPS analytical capabilities lacking among reporting labs. This is a concern because according to the Global Drug Survey, NPS actually poses more danger than traditional illicit drugs. For example, the risk of seeking emergency medical treatment is 30 times higher among synthetic cannabinoid users than cannabis users. So your traditional drug testing using GCMS or LCMS or even LCMS-MS cannot or will not keep up with the rapid evolution of these drug products. However, high-resolution mass spectrometry has features that we think promises a solution to this challenge. HRMS is not new. TOF-MS or time-of-flight mass spectrometry, for example, a form of HRMS has been around since the 1950s, but it's been only in the last decade that TOF-MS has been exploited for drug testing. So TOF-MS actually has a very simple principle, and you probably remember this from your organic analysis courses. In a time-of-flight mass spectrometry, ions obtained from organic compounds, when they're given a voltage jolt in the pulsar of a time-of-flight tube, these ions travel the time-of-flight tube according to their size. The smaller their size is, the faster they are, and hence the time-of-flight of the ion is proportional to its charge-to-mass ratio. The current advances in the optics and the engineering of detectors in this platform has allowed accurate mass measurements up to about the 3rd decimal place of an atomic mass unit. At such level of accuracy, it has become unambiguous to assign a formula matched to an accurate mass measured in a sample, thereby facilitating what is called non-targeted data acquisition. Here are 2 examples of opioids, pentazocine and morphine. Most ordinary LCMS and GCMS has a unit resolution, and since these 2 compounds are practically isobaric, they have the same nominal mass. If they are not chromatographically separated, your single quad LCMS or GCMS will not be able to differentiate between these 2 compounds. However, if you look at their exact masses, the difference between the exact masses actually is much higher than the threshold for an LC-Q-TOF-MS to distinguish between these 2. More recently, the more popular platforms in laboratories are Q-TOF-MS, and in that particular platform, there are 2 types of experiments that you can do. One wherein you do not activate the quadrupole analyzer, in which case all ions that you have obtained from a sample passes through the quadrupole, through the collision cell, and you basically generate parent ion masses for all compounds that have ionized in your sample. Typically, you'll be able to assign formula for compounds in your sample through a thought experiment. You can also activate the quadrupole, in which case you would have to choose, or you could let the platform choose a parent ion, which are then fragmented, or is then fragmented in a collision cell, generating data for fragment ions mass, which gives you a clue on the structure of your compound of interest. Depending on your data acquisition and data analysis workup, you can perform many different types of analysis using HRMS. Data acquisition can be done by targeted or non-targeted manner. If it's used as targeted, it's not any different from your typical LCMS-MS, where you scan for compounds of interest a priori. For non-targeted data acquisition, you basically acquire data for all ions in a sample. So if you've done a targeted data acquisition, obviously there's no other choice but to do what's called a targeted data analysis, and that particular analysis is of course targeted. For non-targeted data acquisition, there are two different ways of doing the data analysis. In fact, for targeted data analysis, there are two varieties. One, if you have the reference standard for your compounds of interest, you can then have a database of the retention times and the exact masses of your compounds of interest. And in the end, you will be able to confirm your unknown. So this is not any different from targeted analysis. An alternative is if you don't have the reference standard, because reference standards can be costly, and NPS literally have thousands of different variations now. You can have a database of the exact masses of your compound of interest. In the end, you will end up with a tentative match or a suspect, which of course would need to be confirmed later on with a reference standard. So that process is called suspect screening. On the other hand, if you are literally guided by peaks of interest in a TIC, where you don't use any a priori list of targeted compounds, the analysis is called non-targeted analysis. So in our lab, we do these three types of analysis. The first two types of analysis is what we call an analysis for known unknowns, primarily because you know that those unknowns could be present in your sample. On the other hand, if you do not have an a priori list of target compounds, you're doing what is called an analysis of unknown unknowns. So just to give more detail on these three different types of analysis, for targeted analysis, again, we have a reference standard available for the drugs of interest. And we create a database of that set of reference standards. In these kinds of analysis, we use accurate mass, isotope cluster, and retention time match for confirmation of an unknown compound. And if the MSMS spectra of the reference standard is available, we also look at matches of the fragment ions in the MSMS spectra. So in my laboratory, we have a comprehensive drug panel of about more than 1,000 drugs, majority of which are new psychoactive substances. In the panel, we have also about 184 drugs of abuse, 118 prescription drugs, and that's actually, we now have about 40 bioactive ingredients of herbal and dietary supplements. Of course, the number of drugs in this panel is a moving target. We are now funded by the DEA in the surveillance, and so quarterly we add about 20 to 50 drugs to our panel. Also, in recent years, we have gained the ability to synthesize our own reference standard if the reference standard is not commercially available, and therefore we also add those to our targeted panel. For suspect screening, as well, I've already alluded to in my earlier slide, here you have a database available, but you don't have a a reference standard available for the compounds in your database. And for confirmation or for determining suspects using this method, we use accurate mass and isotope cluster matching. We also use what is called retention time plausibility. Let me explain this a little bit. With the experience that we had on the different classes of NPS, we're able to develop this compilation of retention time ranges that are expected for different classes of drugs. And therefore, if a suspect, for example, a synthetic cannabinoid, does not match the expected retention time for that class of compound, then the level of confidence that we have for that particular suspect is low. Also, in some cases, the compound may have been published by another group, and if their chromatographic method is similar to ours, we use relative retention time in order to increase the level of confidence in our suspect. So in our laboratory, we have organized suspect and NPS panels for synthetic cannabinoids, stimulants, hallucinogens, and depressants. And the way we organize and the way we assemble the suspect panels is by reading, of course, the literature. We also compile lists of NPS that are published by reference standard manufacturers, research chemical vendors. We even would troll drug discussion blogs and drug discussion websites posing as NPS users in order to get real-time information on what is currently popular among recreational drug users. Also, more recently, there are a number of drugs that are metabolized very quickly by the human body. And for that, if you have a case where we are suspicious of a specific compound that we're not finding the parent ion in the biological sample, we create a database of the predicted metabolites of that particular drug ad hoc and use that for suspect screening. In very few cases, we are able to do non-targeted analysis. This is very involved and it takes a long time. For non-targeted analysis, you don't have a reference standard and there's no specific database that you're able to use. Of course, accurate mass and isotope cluster matching is still useful here, but also retention time plausibility. So we use the mass spec to generate a formula for our unknown, and we also use MSMS spectra searches in open source databases and spectral library to look for potential identity of the unknown if those spectra has been published already. We also rely on silico fragmentation to potentially look at whether the fragment ions that we're seeing in an unknown is plausible. And not only for non-targeted analysis, but for all these other analysis, we rely heavily on what we call toxidrome analysis, where we collaborate really very closely to medical toxicologists and pharmacologists and consult them in our analysis to determine whether what we think could be a potential match to a given case makes sense in terms of the drug class and the known pharmacology of that drug class versus the symptoms that we're seeing in the patient. So let me just give you a brief overview of our targeted analysis workflow. We work with many different biological samples. We use a generic method for preparing the sample in order to cover as a wide variety of classes of NPS. For blood, we use protein precipitation, and for urine, we use dilute and shoot. The extracted sample is then run on an Agilent QTOF LC-MS. And here we perform 4 experiments, one a TOF experiment, another a QTOF experiment, and then we perform both experiments in positive and negative polarity. So what you generate from an LC QTOF MS run is a total ion chromatogram, which is then queried against an in-house personal compound database library. So your TIC would contain pairs of retention time and accurate mass called features. And those features are then compared by the algorithm to our database. In the end, you obtain the results based on retention time match. We typically allow about 0.15 minutes as the threshold for a match. Mass error, the threshold is about 10 parts per million. A target score, which is indicative of the isotope cluster match, among other things. A target score about 70, at least 2 fragment ions in the MS-MS spectra. I'm going to skip this slide. So we've used these workflows in synthetic cannabinoid surveillance that we've done with the DEA between 2012 to 2017. So the DEA collected and referred cases to us. It was our DEA collaborator who would contact hospitals, medical examiners' offices, law enforcement, and the local Department of Public Health to send us samples at UCSF. When we receive the samples, we work on the sample. During the work of the cases, we actually would communicate constantly with the DEA and the CDC, and then later on the Department of Homeland Security to determine whether the tentative match that we have makes sense in terms of the toxidrome analysis that is available for the cases. Later on, because of the rapid evolution of the identities of NPS compounds appearing in the market, we needed to collaborate with a reference standard manufacturer, Cayman Chemical. Still later on, when we started publishing our work, we were approached by a prolific synthetic organic chemist from Stanford University who offered his services in collaboration to synthesize reference standards for us. So that collaboration has been kept, of course, because he provides so much value to the work that we're doing. So I thought this would be a good demonstration of the dynamics of the type of surveillance that we do with the DEA. This is the zombie outbreak that I showed a clip on earlier. So on July 12 of 2016, we were alerted by the DEA as well as our DHS counterpart of the outbreak happening in Brooklyn, New York. The DEA then arranged samples from patients that were in New York hospitals to be sent to us. We worked on the analysis. The initial data that we obtained pointed to a new drug, AMB Fubinaca, and also in some cases, we found just the metabolite of AMB Fubinaca. And at that time, the reference standard for the metabolite is not commercially available. However, we anticipated, so part of the work that we also do is we predict what would potentially be targeted by the clandestine labs, and we would synthesize those reference standards in advance. When we look at our library, we have the acid metabolite reference standard already. So we were able to confirm this drug or this metabolite the same day that we actually detected it as a suspect. So in a matter of about a week, we were able to analyze and quantify the biological samples and report it to the DEA. Later on, we need to match what's in the product that were actually used by these patients to what is in their biological sample. So that's when the Department of Homeland Security stepped in, contacted law enforcement, and arranged for the drug product to be sent to us. We analyzed the drug product, and indeed AMB Fubinaca is in this drug product. So using the type of workflows that we have and our ability to preempt and synthesize anticipated NPS shortens outbreak resolution to weeks or sometimes days. Without the reference standards, typically outbreak resolutions can take months. So between 2012 and 2017, because of our work with the DEA, we were able to trace the molecular evolution of synthetic cannabinoids. And there have been hundreds of synthetic cannabinoids that came out in the United States in that time. What is highlighted in this particular figure are the most popular ones appearing at a time period indicated by the arrow. And so when synthetic cannabinoids first started to appear in the United States in 2010, JWH18 was the most popular synthetic cannabinoid. That structure did not come out of the air. That structure is actually based on cannabinoid studies done by John W. Hoffman, hence JWH, at Clemson University in the 90s, where he was trying to look at cannabinoid-like structures that could potently bind to cannabinoid receptors. JWH1 actually has the optimum structural feature that would increase binding to the CB1 receptor. And so this were targeted then in the early, in the mid 2000s and incorporated in a drug product. So when JWH18 was first introduced, because structure is a little bit different from THC, the active ingredient of marijuana, this is legal because in the United States, because of how the drug law regulations are structured in the United States. Later on, it has caused and it has been associated to intoxications, and therefore it was temporarily scheduled. Once it was temporarily scheduled, what the clandestine labs is simply to replace the hydrogen at the end of the pentyl chain with a fluorine, and the resulting compound AM2201, when it was first released, was considered legal and therefore can be abused. It became illegal or temporarily scheduled, and by the summer of 2012, the American Congress thought that they would be smarter in their in the way by which they would pass the laws for temporary scheduling. So what they did was when they scheduled AM2201, they also mentioned that if you lengthen or shorten this pentyl chain or substitute it with other substituents aside from fluorine, that will be considered scheduled as well. And also, if you put any substituent in the naphthalene ring, that will also be considered scheduled. So what did the clandestine labs do? These are smart people. They're actually organic chemists also. So what they did is they got rid of the naphthalene ring and replaced it with a cyclopropyl ring, and voila. This is a structure that does not have, it's not covered by the regulation in 2012. So what most of the clandestine labs have been doing since then is simply play around with the different functional groups in the structure. So what I did here is really to highlight in red the structural changes that are happening in the synthetic cannabinoid scaffold. And if you look at the AMB fubinaca, which was found in the zombie cases, compare it with the first type of synthetic cannabinoid, there's really not much similarity in the structure anymore. Only this carbonyl group and this specific methylene group was preserved. And yet, if you look at the EC50 value, and the EC50 value is included here, primarily because I want to stress one point here. If you look at the EC50 value to human cannabinoid receptor 1, you're seeing a structure that is more potent in terms of its ability to bind human cannabinoid receptor 1. And in fact, what has been happening from 2010 to 2017 with scheduling is you're actually pushing the clandestine labs to produce more and more potent synthetic cannabinoids. And we're seeing it in the field because in JWH, in the time where JWH18 is the popular synthetic cannabinoid, we're not seeing deaths in mass outbreaks. But by the time that we have AMB fubinaca and 5-fluoro-ADB, we started seeing deaths. So this collaboration, this work actually produced 5 or 8 different compounds for which data from my lab was used by the DEA to schedule or put these drugs on temporary schedule. The surveillance work ended in 2017 because it was not funded, but our collaboration was renewed in 2019. And this work has now been expanded to all different types of NPS under a program called Detox. So one thing that I want to emphasize in our current work is that we have seen the importance of preempting the NPS that will come out of the drug market. And the reason behind this is that we have gotten tired of losing the battle between the clandestine labs and us. We're almost always basically chasing them. And that's the reason why we've started synthesizing what we call prophetic NPS. Now that work has been expanded not only on synthesizing the compounds, because we've realized that there could be thousands of different targets, and yet, we can only do so much in terms of what we can potentially prioritize and have a stockpile of all those compounds that would have a higher probability of causing a mass outbreak. So what we've done my collaborator from Stanford has moved to the University of Sydney. He's continuing to synthesize NPS, but we've also expanded this work to include cell pharmacology and animal pharmacology, so that we can screen the libraries and determine which ones have a higher binding affinity for the cannabinoid receptor, and prioritize those in animal studies so that we would know which ones could have the ability to actually cause most harm, and really prioritize the synthesis of the metabolites of those compounds as well. At UCSF, we've also collaborated with the COCA lab. And the reason for doing this is because some of these cannabinoids or some of this NPS we think might have off-target effects. Synthetic cannabinoid, for example, can cause acute kidney injury. You don't see that in marijuana or THC. And so there must be some off-target effects. And we think that the model that's being used by the COCA lab can actually allow us to determine what other types of receptors are targeted by by synthetic cannabinoids. So for prophetic NPS, I've already mentioned that NPS are intelligently designed, and so future NPS targets can actually be predicted. So really, if you look at the structure of most synthetic cannabinoids, you can divide the structure of synthetic cannabinoids into 4 pharmacophores. You have the head, the linker, the core, and the tail. So what we have done is to look at synthetic cannabinoids that have been released in the market and look at the different cores, the different linkers, and the different tails and heads that have been used by clandestine labs, and anticipated other core structures and other possible heads that can be used. And using synthetic organic chemistry tools, we're able to synthesize a library of prophetic cannabinoids. We're also able to actually characterize their pharmacology. So that was actually what happened in the zombie cases. The reference standard for a compound that we detected in July 2016 was already in our lab since February of 2015. So I said about the animal pharmacology, we use AT20 cells transfected with the human cannabinoid receptor. We use a fluorescent reporter assay. When there is a cannabinoid receptor activation, there is a decrease in fluorescence, and we normalize our results with known binders of the HCB1 or HCB2 receptor. And so we use this assay to actually look at the binding affinities of the different prophetic NPS we synthesize. Here, this has been normalized to Win55.2.2. And we've noted here both the relative maximum that we obtain compared to Win55.2.1.2.2, and also look at the EC50 values. And there is a trend that's starting to show up, or has started to show up, which is, I think I've mentioned before, there is a trend in increasing potency over time of this compound. As you can see, the binding curves are shifting to the left. We noted the position of where the JWH18 binding curve is, but also the maximum efficacy of the latter generation are higher. So you can actually generate up to about 150% max for AB Fubinaca. And then for the animal pharmacology, we use the Y-star rat model to look at the rodent cannabinoid triad. We place a probe on the rat, dose them with different doses of the candidate synthetic cannabinoids, and we monitor their mobility, their temperature, and their heart rate. And so here's just an example where if you compare THC, for example, here we're looking at body temperature. If you dose the rat with about 3 mg per kg of THC, then you see this lowering of the body temperature that then recovers. So what's striking about some of these compounds is that they can lower it even more than THC, but also the recovery time is much slower. I'm gonna skip this slide because I think this is just another surveillance study that we've done. I think what would be more relevant is, how about the Philippines? So in 2017, Dr. Willie Padolina, when he learned about the work that we're doing at my lab at UCSF, has encouraged me to collaborate with a lab at the University of the Philippines. And so since then, we've been trying to help UP Manila to set up what is called the UP Drugs of Abuse Research Lab. And by the end of 2018 to 2019, we were curious and get a sampling. We got a sampling of cases from Philippine General Hospital who may have been intoxicated with drug. And so, mind you, a lot of these cases, because they are from PGH, are from low socioeconomic status. And so we thought that maybe NPS may not be relevant to this population. However, we confirmed about 71 cases with NPS. Majority, as we expected, are traditional illicit drugs. But in 38 cases, we found NPS. And in fact, in 11 of those cases, we only found NPS. For those where we found NPS, some of them have only one NPS class, and some of them have two NPS classes. And for those with one NPS class, for cathinones, we found bifedrone, methcathinone, butylone, and energy-3. Now, these drugs, remember, these are 2018 samples in the Philippines. These drugs were predominant in the United States between 2012 to 2017. So we're a little bit late in the United States in terms of cathinone. But what is interesting is that the cannabinoids that we found in this particular patients are actually this is a metabolite MDMB fibrinata and 5-fluoroepirapine. These are drugs that we're also finding in the United States in 2019. So we're updated with cannabinoids, but not so much with cathinone. But this is really a shocking finding even for me, because I never thought that NPS is already in the Philippines. In some of these cases where you don't have where you have more than one NPS class, you have a combination of different classes of NPS. So I started to talk, thank Sam Bannister from the University of Sydney, who has been instrumental to the synthesis of the prophetic NPS. I'd like to thank some of the members of my laboratory who have been working with us incessantly to develop and validate methods and add more NPS in our panels, and work with different collaborators from the DEA, the CDC, University of Colorado, UCSF, and now with UP Manila. Sorry, I'm over time.
Thank you very much, Roy, for that very exciting talk. So we are now ready to entertain questions. I'm sure there's a lot of questions from the audience.
There's one from Ronilo Flores. He raised his hand earlier. O'Neill, is Ronilo Flores still there? So while we're waiting for O'Neill, so I have a question, Roy.
Sure.
So you mentioned that you're doing synthesis in advance, right? So have you considered that those street chemists will apply their knowledge of medicinal chemistry approaches like using non-classical isosteric replacement of some of those functional groups in your drugs?
Yeah, so that's a really very good question. In fact, that really points to the the ethical dilemma that we have when we were starting this work on synthesizing NPS. So as I've mentioned, the start of NPS is really a lot of this clandestine labs with synthetic organic chemists referring to previous literature and looking at what have been synthesized by cannabinoid studies, for example, and just copying the synthetic routes. These are simple synthetic routes for these drugs, and then putting that in their product. So we made this agreement between me and Sam and some of our collaborators that the NPS library is actually not published. So we hold the NPS library in our in our laboratory, we don't publish them, and we only publish the compounds that after it has hit the street already, so that we're not adding on references for these clandestine labs to actually use in order to come up with new drugs. It's really at the start, the only, because initially this work is not funded, and the only incentive that Sam has in actually doing this with us is that you can get more publication. But also we're both very interested in this topic, and we do understand the ethical dilemma that us and the medical toxicologists, especially our collaborators at the DA, have. And so we just made that agreement. The reason why we're doing the pharmacology work also in advance before this compounds hit the street is that we wanted to be very helpful to medical toxicologists. And the reason is this: whenever a new drug is published as a case report, it's probably good that the medical community is aware that that drug has come out, but it doesn't really add much knowledge to the medical toxicologist because the pharmacology of that particular drug is not known. And so, their guess is as good as ours regarding the pharmacokinetics or the pharmacodynamics of that new drug and its relative toxicity. So what we have done now is that we have compiled the pharmacology of a lot of this anticipated NPS. And whenever we have a case where we actually see a drug in our anticipated library, when we publish the case report, we also give some added value to the case report by publishing what is known about the pharmacology and the toxicity that we have done our studies on in advance.
Thank you, Roy. So follow-up question to that. So can the enforcement agency can they do a scheduling of that future drug, or?
That's a very good question. So that has always been the debate, right? So why not just schedule all of them, right? I mean, you sort of have that exemptions, right? So for example, for opioids, right, morphine is scheduled, but you can also use morphine under the medical setting. So that is an exemption, right? So the reason why that is that if you schedule something that you can easily do that for something that is already known, right? But for something that you don't know yet, so for something that you're anticipating to be hitting the street, if you schedule that, you will also be inhibiting research on that. And why is that important? Well, for synthetic cathinone, for example, bupropion is actually a cathinone. So it is a bath salt. If you think of bath salts as synthetic cathinone, bupropion or Wellbutrin, which is a drug, that is an NPS, if you'd like to consider that, since it's a cathinone. There are legitimate medicinal properties to some of these drugs. The only exception that the DEA has done is on the phentalogs. And the reason why the phentalogs have this sweeping scheduling is because it's relatively more toxic than a lot of the NPS. Carfentanil, for example, has about 10,000 times the potential potency as morphine. And so really in the phentalog space, they have made that exemption, but for all the other drug classes, I think it's balancing between protecting the public, but also not impeding research on the potential medicinal properties of some of these drug classes.
Hi, Roy.
Thank you.
There's O'Neill. O'Neill already put his question on the Zoom Q&A. Right, O'Neill is a professor here at the UPLB Institute of Biological Sciences. So he's saying, thank you for your exquisite presentation. Your work is something that is important if you want to address the problem of of neuropsychotic drugs in the Philippines. He says he's particularly interested in the binding receptors for cannabis. Would treatment with tunnamycin or other glycosylation inhibitors have an effect on the expression of the binding receptors?
I am not sure I would know the answer to that question. What we have done for most of the binding studies that we've worked on is really just to assess in vitro binding affinities. And even with in vitro binding affinities, that does not usually translate to in vivo effects. For example, XLR11 is a synthetic cannabinoid which has a lower binding affinity actually than most synthetic cannabinoid to cannabinoid receptors 1 and 2. And yet, among the synthetic cannabinoids that we have studied so far in the drug surveillance that we've done, it is XLR11 that has caused acute kidney injury. And so the in vitro binding assays that we do for anticipated synthetic cannabinoids is really just a screener for us in order to focus our work on what could be then studied in vivo and see whether those with high binding affinities to the receptor would actually cause intoxications that might be of interest because they could potentially cause mass outbreaks.
Yeah, it's interesting that that when you look at the potency, and of course that's related to the binding affinity, right, of the singular synthetic compounds, they're definitely increasing, right? Do you think there's a modulation effect? You know, if you smoke marijuana, right, without and instead of ingesting THC, do you think there's a modulation effect that's happening if you combine, a lot of these compounds with its natural counterparts, well, from a holistic perspective?
Yeah. So this idea of synthetic cannabinoids comparing it to marijuana is a little they're not really the same in the sense that when you have a synthetic compound, you're really just exposing yourself to that single synthetic compound, like for example, WH18. When you have a sample of marijuana, it just doesn't have GWH18 there. There is cannabidiol, there's cannabinol, and there's this host of other natural products that can potentially modulate, as you said, the effects of the psychoactive ingredient. And so that is probably the reason why the effects are different between the synthetic cannabinoids and marijuana. On top of that, we do think if you look at the structures of the synthetic cannabinoids, so you see an indole or indazole, and if you look at the symptoms that we have seen so far in a number of these outbreaks, there are symptoms that you don't necessarily find in marijuana intoxication. And so we do think that, THC, the psychoactive ingredient in marijuana, targets the CB1 and the CB2 receptors. A lot of the synthetic cannabinoids, they also target the same receptors, but we do think that they actually also are able to bind to other receptor, thereby facilitating other potential toxic effects. And that's another huge difference between these two different groups of compounds.
Okay, thanks, Roy. Mm-hmm. Anything from YouTube, Jeff?
Yeah, we have one question, po. So it's from Connie Remorosa. So she says, excellent talk, sir. How would you ID isomeric compounds when the high resolution tandem mass spectra are almost similar?
Very good question. Well, isomeric compounds actually would have the same parent ion mass, right? And so there are two ways by which you can do that. One is to look at the fragment ions, if the fragment ions are available. Sometimes even the fragment ions would be very difficult to actually use in order to differentiate the two. The other way of doing that is by chromatographic separation, right? So if you have chiral columns, probably that might be able to address that. We have cases that we've done where and so the other question is that relevant at all? So if you have two isomers of an NPS, would one isomer be more potent than the other? And the answer is yes, for some of them. Sometimes the para isomer could be more potent than the meta isomer or the ortho isomer. And so in some of those cases, we've actually referred the case to another group that has access to an NMR, and they're able to put more information to what we already have from the lab. So yeah, so although HRMS is a good platform, obviously it's not going to answer all the cases that we're working on. Sometimes it would really require other platforms.
And so there's just like one more question. It's my question. I mean, I'm not a pharma expert, but I'm quite curious about how you guys prioritize the evaluation of your prophetic and NPSs. Like I heard that binding affinity is one of the prime considerations. I was actually just quite curious if you guys are balancing out your prioritization with the ease of the synthesis, because like anticipating the probability of something being rolled out into the streets. Baka po yung mga tamad lang. Perhaps there are just like the lazy routes towards something that works, which might not be as potent as like the strongest binding candidate. That could potentially hit the streets much faster or much sooner.
So the ease of synthesis, we sort of evaluate that by looking at the trends, right? So you're right that sometimes maybe the ones that are easier synthesized would potentially be targeted more than the ones that would have complicated synthetic routes, and that is the reason why we troll discussion groups of drug discussion groups, because we really want to know as a surveillance group what is out there. And by looking at the trends and what particular functionalities are coming out of the recreational drug market, we're able to put more priority to some of those that we think that this is, this particular functional group is coming out more and more often. And therefore, even though we have not completed the pharmacological study of those particular compounds, we may want to prioritize them now because we're anticipating that there might be more iterations in the structure that would come out.
Yep. Thank you.
There's another question here, Roy, from the audience. So the question is there an ongoing or at least in the making collaboration between your group and the UP Manila group with the law enforcement agencies in the Philippines? So
we already have collaborations. Well, of course, we have a collaboration with UP Manila, and we're actually advising them. In fact, we train them on the use of HRMS. They sent chemists and pharmacists to our lab. We train them, and then we're setting up the lab in UP Manila. When we set up the Drug of Abuse Research Lab, the first thing that we did is really to reach out to different agencies in the Philippines, like PDEA, for example, NBI, all the potential stakeholders in the Philippines, so that they're aware of this effort. And really, the role that we think the Drugs of Abuse Research Lab would take in the Philippines is, in a sense, be able to support all these other government labs that are doing or conducting the drug testing. So unfortunately, those plans have been delayed because it's a little bit difficult to get reference standards for the lab, and also we've been delayed by COVID-19. But those potential connections are ongoing. In fact, I think some agencies would want to have samples already analyzed at the UP Drug of Abuse Research Lab. At this point, the method is being validated by the group of Joanna Turalba at UP Manila. And but they're able to a limited extent, they're able to analyze cases for PGH. Once those methods have been validated, I think they would open up the analysis to other agencies in the Philippines.
Okay, thank you, Roy. I think maybe one more question here. There's another question. So have you tried to study other herbal plants in the Philippines, aside from marijuana, which have high psychoactive activity?
No, we haven't, but we will be very open to potential collaborations if there are groups that are interested in actually doing that. We have herbal bioactive ingredients, which we have incorporated in our panel, just because interactions between some of those small molecules with drugs can potentially lead to certain pathophysiologies. But we've never looked at indigenous plant materials coming from the Philippines.
Thank you, Roy.
Okay, so I think that's it for the open for the questions for Dr. Gerona's seminar.